Okay, so the lecture is going to be relatively short. It's probably going to be around a half hour or so. I just want to talk about what a memory register is and then lab 5. Okay, because once you know what a memory register is, you'll be able to do lab 5. Now, the priority is lab 4 if you haven't finished that yet, because lab 4 is due this Friday, November 3rd. Is there anyone that's finished lab 4? A few people? Okay. Yeah, I would expect a few, right? I wasn't expecting many, but that's good. If you have completed lab 4, then yeah, you can start into lab 5. Now it's not due until a week from this Friday, okay, November 10th, but you know, it's always good to start these labs early if you can. Okay, so where I want to start with is from last time, we talked about what a D flip-flop is. Okay, remember a D flip-flop, that's a memory device. It's an edge-sensitive latch, like all flip-flops, and it can store a single bit. And this is the Verilog, system Verilog code that you need to model a D flip-flop. You're going to need this for lab 5. Okay, you know, I would take a picture of this. If you haven't taken a picture of this already, I would, because this is what you need. You just got to, you know, declare your inputs and outputs. And again, remember that anytime you have an output within an always, right, either always FF or always comb, you got to put logic, right, where you define that output, you know, output logic, and then the name of the output. Okay. Also recall that, you know, one way to create a latch is by having an if statement that doesn't have an else. Okay, so you know, if reset's active, and these are all active high inputs, and they're all synchronous. So if reset's high, we're going to reset the flip-flop by making Q 0. Right? If we're not resetting, but we're setting, we'll then reset Q to 1. If you don't reset or don't set, and you enter, now remember, enter is the same as enable or load. So if you're not resetting and you're not setting, and you enter, that's going to assign Q to whatever the D input is at the time of the 0 to 1 transition of the clock. See, this is all happening since all these inputs are synchronous. It's all happening on the rising edge. Right? Remember that you know, the way this always FF block works is that whatever you put within these parentheses, when that changes, you know, when that happens, this positive edge happens, that's when the inside of that always FF gets evaluated. So that's when the if statement is going to be evaluated. Okay. Now, when you leave out an else from an if statement, that creates the latch, right? So if you're not resetting, you're not setting, and you're not entering, you must be saving. Okay, where the next state of Q is just going to equal what Q is now, right? It's going to retain that Q value. Okay, so any questions about the D flip-flop before we move on to a register? Now, also, this is the high-level black box diagram for this D flip-flop, right? Single bit D input, single bit Q output, and then your clock is always a single bit. Do you remember what this little like triangle on the symbol represents? Kind of talked about it briefly last time. You might have missed it. Did anyone catch what I said? Am I going to go like 0 for 82 on this? Because nobody in my other sections caught on to it. I guess I went over it too fast. But this little triangle, that just indicates edge sensitivity, right? Because remember, a flip-flop is a latch that's edge sensitive, right? Again, the edge sensitive is referring to whether it's rising edge trigger or a falling edge trigger. So anyway, that little triangle just means it's edge sensitive. All right, so the new material today is what a memory register is. And a memory register is just made up of multiple flip-flops, because a memory register will store multiple bits as opposed to a flip-flop that just stores a single bit. Okay, so here's an example of a 4-bit memory register. It has 4 D flip-flops because each D flip-flop stores a single bit, right? So if you put 4 of them within the same device, well, now you got a register. Okay. In your CPE 233 class that you'll take after this one, that microprocessor that you'll build, it has 32-bit memory registers, right? So it's got 32 flip-flops. And notice how the flip-flops are connected together. The D input of each one goes to a main D input that's 4 bits. So if you think back to the adder, right, the RCA, remember how you had, 4-bit A coming in and 4-bit B coming in, and then it split up and like A0 went to one of the adders and A1 went to another one and so on. Same sort of thing here, right? You got a 4-bit D input, D0 goes to one flip-flop, B1 goes to another one, B2, and B3. And then on the output side, it's the same thing like the sum output of the RCA, right? Where all the sum outputs came together into a 4-bit main sum. Well, the Qs do the same sort of thing here. So Q0, Q1, Q2, Q3, they all come together and make a 4-bit main Q output. Okay, so the structure of this is very similar to the RCA. It's just got flip-flops here instead of adding circuits. Now, what's different with the register compared to the adding circuit you did previously is the register, because it's sequential, it has a clock input, right? Your adder, your RCA had no clock input because it wasn't sequential, it's combination, right? There's no storage in an adder. Okay, so anytime you have a sequential type of circuit, it's going to have a clock input. And most often, the clock inputs are connected together. So you see all the clock inputs of the D flip-flops are connected together to a main clock input of the register. And the reason why the clock inputs are all connected together is that puts all these flip-flops in sync. It puts them all in step, right? They're all going to be storing data at the same time. They're all going to be resetting at the same time. They're all going to be loading at the same time. They do everything together, okay? Because their clocks are connected. Okay, does that make sense? Okay, so any questions up to this point? Well, actually, before you have any questions, you should be able to tell me now what the high-level black box diagram of the memory register looks like, right? This is how the flip-flop looks like, right? How would the memory register high-level black box diagram look? Like, how would it compare to the flip-flop?
Wouldn't it be the same instead of D and Q are both 4 bits?
Yeah, exactly. Exactly right. Still got your clock. It's a single bit because the clock is always single bit. But yeah, your D and your Q would now be 4 bits instead of a single bit. That's the only difference. Okay, now you're gonna love this. Okay, the next thing you're really gonna like. Because think back to the RCA that was made up of those 4 adding circuits, right? That connected all together. How did we model that? How did we model the RCA? Like, what did we do to take those single adding circuits and then make it into an adder? It was in lab 2 and lab 3, because lab 2, you had the 3 full adders and the half adder, right? Then lab 3, you still used the same RCA as lab 2, but then in lab 4, you made it all full adder. Okay, but what did you have to do to connect all the adders together? Make the RCA, like you had your individual half adder, your individual full adder. But then what else did you need to model it? Well, the internal signal, yeah, because you had to connect everything together in the structural model, right? Remember, there was a whole nother design source that connected all the lower levels together. Well, you could do the same thing here, right? You could, after you model your single D flip-flop, you could then have a top module that makes all these connections. Okay, you could do it that way. But instead, we're going to have you do something different, because instead, we're going to have you let the software do that. And because see what you can do instead of doing that top module like you did with the RCA to connect all the individual low modules together, instead what you can do is take this same code that you modeled the single D flip-flop with and just make some edits. One edit that you would have to make is now declare your D input as 4 bits instead of a single bit. So you would just, have input 3 to 0 D, right? So, for a single bit, it's just input D, All right, but all you would have to do is just take the same code and just declare your D input as 4 bits instead of a single bit. Also, your Q output. Now, what am I gonna have to add here since the Q output is within an always FF? Logic. Yeah, you gotta put logic in there, so you would be output logic. And then 3 to 0 Q. And then the only other edits you have to make is now instead of assigning Q 0 and it's reset, because here it's the single bit for the single D flip flop. When you make it a register, now you just got to change this to 4 bits, right? Because now Q is going to be 4 bits instead of a single bit. And you'd have to do the same thing here for set, right? You'd have to have it, Q less than equal than 4 tick mark B all once, 4 once. Okay, so what the software will do, what Vivado will do, is it will recognize that you want to make a register, that it will recognize that you just want to replicate these flip-flops 4 times because it understands that a register is, flip-flops with their D inputs connected together and their clocks connected together and their Qs that come together. So the software will do it for you. See, we could have had you do this for the RCA when it was made up of all full adders. You could have just taken the full adder code and just made the inputs multiple bits and the output multiple bits. And the software wouldn't have made the RCA for you. It would have made those connections that you did essentially manually in the top mark. Okay, but we didn't tell you that at this time because we wanted you to get practice with, doing structural modeling. Okay, but for Lab 5, this is the way we want you to approach the register. So, see, the good news is, and the reason I thought you'd be jumping for joy right now, but I understand you're tired from the exam and you don't want to exert yourself. But see, what this, the consequence of this is that once you have a working D flip-flop, all you have to do is copy that code, right? Put it in another file that you call a register, and then just make some edits. You got to make basically 4 edits, and then test that, and you're done. Okay? You look like you have a question. Do you have a question? Oh, you just look like you had a question. Okay, so any questions up to this point before I move the camera and talk about Lab 5? No questions? So it seems pretty straightforward what to do to get a D flip-flop and a register built. All right, let's move on. Oops. All right, so this is where you should refer to the handout. Okay, there should be enough of these handouts at each table for each person. Okay, and it's a double-sided handout. It's got this diagram on one side and this diagram on the other side. So this is the overall circuit for Lab 5. In Lab 5, you're taking most of what's in Lab 4 and you're adding memory, and you're also adding a module that we give you the code, Dr. Mealy designed it, that does time multiplexing. Okay, and what time multiplexing allows us to do is to put data on all 4 7-segment displays at any given time. See, the way those 7-segment displays are connected, the way they're hardwired, is they're basically hardwired in parallel. So without a time multiplexer, the 7-segment displays are going to show the same number. For example, in your Lab 3 or Lab 4, where you have that mux that either passes through all ones to blank all the displays, or the 1110 that only lights up the furthest to the right display. Well, if you had made the data all zeros, like 4 zeros in Lab 3 or Lab 4, all 4 7-segments would light, but they would all show the same number. Whatever the result was, they would all show the same. Okay, it's not possible without time multiplexing for those 7-segment displays to show anything else but the same number. So what Mealy's module allows us to do is that if we had a result. Okay, now your add or subtractor is not going to give us a result like this, but when you do your final project individual, when you do a 4-bit multiplier, you could get, a number that's multi-digit. Okay. Well, what the multiplexer will do, if say your result is 1,279 like this, is that it will display the 9 on the furthest to the right display. Then sometime later, it displays the 7 on the next display to the left. And sometime later, it displays the 2 to the third to the left display. And then sometime later, it'll display the 1. And then it just keeps doing this, right? It displays the 9 here, the 7 here, the 2 there, the 1 there, and it goes back 9, 7, 2. And it just keeps doing this. But it does it at such a fast rate that our eyes don't detect that it's going 9, 7, 2, 1. We just see a steady number. Okay, so that's what time multiplexing is. It's using hardware that's connected in parallel, but showing data at such a rate, as I just described, that our eyes can't detect. Detect the actual. We can't detect the actual time multiplexing. We just see the steady number. Okay, and the reason we give you this code is because if you take a look at it, if we give you the text file, we don't give you the actual file, we give you the code in a text file, and you have to copy and paste that code into a design source file. And Mealy, Dr. Mealy, he wrote this in Verilog, okay, instead of System Verilog. So that's one of the things you got to watch out for, is that when you go to copy and paste the code from the text file, when you create the design source, okay, when you're designing or creating your design sources, make sure to choose Verilog and not System Verilog. If you choose System Verilog and you put that Verilog code into that System Verilog file, you're going to get all kinds of errors. You're going to see red lines everywhere. Okay, because Verilog does not use logic like we do in System Verilog. You know how we use logic to declare internal signals? In Verilog, they use the word wire. And then logic here, when we have an output within an always block, like we do in System Verilog, in Verilog, they use reg, R-E-G. Okay, and then there's some other differences, like in Verilog, you don't have an always FF block, it's just always, and you don't have an always comb, it's just always. Okay, so there's, there's half a dozen like main differences. There's probably other ones that aren't as common. But the key thing is, for this lab 5, just make sure that you create a Verilog file for Mealy's code. You see, Vivado will run mixed files. Like all your design sources, like your flip-flops, your register, the top module that you use to connect this all together, that's all going to be in System Verilog like you've been doing. Okay, and Mealy's module is going to be the only one in Verilog. But Vivado will run mixed files. It'll run just fine. In fact, later on in the quarter, we give you some additional files of Dr. Mealy's where he wrote the code in VHDL. And VHDL is a whole nother software that's used to model hardware. In fact, we used to teach that before Verilog up until about like 10 years ago, I guess. Okay, so, but you can have VHDL files, you can have Verilog files, you can have System Verilog files, and Vivado will run it all together just fine. That's one of the things that actually does well. But we usually don't have a problem with that. Okay, so let's come up with the high-level black box diagram for this lab 5. Okay, so looking at these diagrams here, because notice that lab 5 has a lot of what you did in lab 4, right? This diagram here is the lab 4 diagram. But notice we delete some things. See, in lab 5, you're not going to use the binary to hex decoder. You're not going to use the neg output, and you're not going to use this mux that was being controlled by the validity checker. Okay, so where you see an X, that's all going to be deleted for lab 5. So lab 5 is this portion of lab 4 that's not X'd out, plus what you see here. Okay, because on this diagram, you have 3 modules that are registers. You got a 4-bit register and then 2 single-bit registers. Now, this is where, you know, it's a little just semantics, I guess. As we said earlier, a register is made out of multiple flip-flops because it can store multiple bits. So really, if you're only storing 1 bit like these bottom 2 modules are, you don't really call it a register. I mean, I guess you could call it a 1-bit register, but by definition, 1 bit just means a flip-flop. Okay, so even though it does register for those, you know, the middle one and the bottom one, it's really just a flip-flop. You know, it's just going to be this. Okay, so, you know, you're going to have basically a lot of what you did in Lab 4, and then you're going to add memory along with the time multiplexer. So looking at these diagrams here, you should be able to tell me what the main inputs are going to be for our Lab 5. I call it, well, actually, I erased it, but, you know, I call it the adder, subtractor, memory. Right? And again, it's basically Lab 4 with memory. So what main inputs are we going to have?
A, B sub and clock and clear.
There we go. Let me catch up to what you said there. Okay, so yeah, AB, because we're still adding the 2 4-bit binary numbers or subtracting. So we need the sub to tell us, you know, whether we're adding or subtracting. Then what's the other 2? I think you said.
Clock, enter and clear.
Okay, yeah. Yeah. Yeah, see, A, B, and sub, you know, those come right from looking at this Lab 4 diagram, right? Remember, outside the dash box, that's your main inputs. Now, what was a little harder to see perhaps is that on this diagram, the clock, enter, and clear, they're also going to be main inputs because that's what's going to control your memory. So you got 2 4-bit inputs, right? The numbers are either adding or subtracting, and then you got 4 single-bit inputs. Enter is the same as enable or load. Okay, when you enter, that's going to assign whatever's on input D to Q. Clear is the same as reset. Okay, so when you clear it, it's going to force the Q output to go all zeros. And then notice that set, while an input to a flip-flop, is not a main input. And I'll explain why the set is necessary coming up in a little bit. Actually, it'll be towards the end of the lecture. All right, but how about the main outputs? What main outputs do we have for Lab 5? Looking at the diagram here. The seg and anode. Yep, seg and anode, just like Lab 4, except there is one difference. Do you see what's different about the outputs for Lab 5 compared to Lab 4? Because Lab 4 you had seg and an also.
Like seg and 8-bit.
Right. Yeah, remember seg was 7 bits. In Lab 4 here, it's 8 bits. An is still 4 bits, right? Because remember, an, that's what's controlling whether the display is on or off. And there's 4 of them on the basis board. So an is always going to be 4 bits. The reason why seg is 8 bits for Lab 5 and not 7 like it is in Lab 4 is because Mealy's module, the time multiplexer, it uses the decimal point. Okay, so the decimal point is the added seg. I don't know if you noticed, but in the constraints file where the segs are, you know, you might have noticed that one of them is labeled DP for decimal point. Okay, so that's being used by Mealy's module. Okay, so any questions about the high-level black box diagram, right? Because this gives you your main inputs and main outputs for the overall design. Right, so you're going to need that for the structural model when you connect this all together. And I don't know if I said this earlier, but in case I didn't, what I would do in this case, when you get to the point where you want to connect this all together, since a lot of it is like Lab 4, just bring over your Lab 4 top module and then just edit it. You know, because a lot of it will be done for you already. And provided that your lab 4 worked, you know it's good, right? A lot of times you'll have something that works, and if you try to repeat it, you know, you make a mistake somewhere. So it's always good to use modules that you know are good and then edit from there. All right, so this is my suggested order for lab 5. The first thing I suggest that you do is create the D flip-flop, right? Again, you got most of the design source code right there. Then test it, right? You'll need a sim file, test it. Can you think of test cases that you would need to test this? Give me a test case. What do you want to make sure works on this? What is a D flip-flop supposed to do? Say it again. Right, store a bit. So you would want a case where you're not resetting, you're not setting, you're not entering, and you want to make sure that the output stays the same, that it retains whatever it was previously, right? If it was a 0 before, it should be a 0 after. If it was a 1 before, it should be a 1 after. What else do you want to test? Remember, in test cases, you're putting inputs, right? Different values of inputs. So what in this D flip-flop besides storage do you want to test? I can think of 3. They're right there in the if statement.
Reset site.
Yeah, exactly. Right. You want a test case that makes sure it resets, right? So you reset the 1, everything else is 0. You want a test case to make sure it sets. You want a test case to make sure that when it's loaded or when it enters active, that whatever's on the D input gets assigned to Q. Also, you want to check priority. Remember we said the priority is reset, then set, then loading. So how would you check to make sure that reset's the highest priority?
Set to 1 for the same.
Yeah, just make all your inputs equal to 1, right? And make sure it resets. Did you have a question or? Speak mic. Oh, okay, okay. All right, so let's see. So that's testing the D flip-flop. Now, as I said earlier, since you're modeling the memory register, the 4-bit memory register with the same code, except you're making these few edits, you know, like 4 edits, the way you would test the memory register is with the same test cases as with the flip-flop, right? Because you're testing the same thing. The only difference between the register and the flip-flop, register's 4 bits, flip-flop's 1 bit. That's the only difference. Other than that, they operate the same.
So for the additional test cases that we add for the set, reset, and enter, that's just for the simulation, right? We can't like test that on the board.
Well, you'll be able to test resets the same as clear. So you'll be able to test that on the board. Yeah, maybe if you use clear here, you should probably use clear. Like, yeah, this wasn't good what I did. You know, technically, since I called it reset here, I should call it reset there. But for nothing else, for an academic reason, you know, just to drive home, they're the same, even though I didn't intend that. But you should really name them the same. But they do the same thing. When you clear it, the output should all go to 0. Okay, so and that's going to be on your board. Also, enter is going to be on your board. Now, set is not on the board because it's not a main input, but I'm going to explain why we needed set. That's coming up probably in about 10 minutes or so. Okay. All right, so where are we at? So yeah, create the D flip-flop, test it, create the memory register, test it. Now, this is something new. When you test a sequential circuit, no matter what it is, it's going to have a clock. And you have to generate that clock signal in the sim file. Okay, so see, this is new because everything prior to this was combinational, didn't have a clock, right? So you didn't need this for combinational. But now, since we have something that has memory, right, a flip-flop and a register, in your sim file, between the UU2 line, right, you know, where there's that line where you put the file that you're going to test, and UUT for unit under test, and you start doing all your connections between the design source and the sim file names that you have. Well, in between that and where the test cases begin, you want to put this code right here. This always begin Here's the end for the begin, and then within the always, you have the following: clock equal 1, then number sign 5, and clock equals 0, then number sign 5. Now, you should know what the number sign 5 means, because when you're doing your test cases, you know how you have number sign 10, right? Test case, then number sign 10, test case, number sign 10, test case. So what does the number sign 10 represent? We've talked about this. I'm sure we talked about this. Yeah, exactly. Yeah, the number sign 10, the number that follows the number sign, it tells you how many nanoseconds. So the reason you put number sign 10, then a test case, number sign 10, then a test case, and so on, is you're separating each test case by 10 nanoseconds. If you didn't have that, right? If you didn't have the number sign 10, then all your test cases on the timing diagram would be on top of each other. And it would just be unreadable, or probably wouldn't even run. Okay, so that's what the number sign 10 is doing. It's separating those test cases by 10 nanoseconds. Well, here what we're doing in this always block is that we have this clock that we're setting to 1, and then we're going to leave it 1 for 5 nanoseconds. Then it's going to go to 0 for 5 nanoseconds. And then anything within an always block, it just runs forever. It just runs for infinity. Okay, so this is just going to keep going along. Okay, so this code will generate on your timing diagram, it will generate this periodic square wave, okay, that we call a clock. Now, what is the period of something like this? What is the period of this square wave that's high for 5 nanoseconds, and low for 5 nanoseconds, and high for 5, low for 5, and it just keeps doing the same thing? What's the period of that? 10 seconds. Yeah, just 10, right? You all learned about period of a waveform in physics, and I'm sure you've seen it in an EE class at some point. You've had an EE lab, right? This is the period, right? It's just the time it takes for a waveform to repeat. How do you get frequency from period? Just reciprocal, right? Frequency is just 1 over period. So the frequency that we're running this clock at is just 1 over 10 nanoseconds. What's nano? 10 to the what? -9, right? Not -6. People always confuse nano and micro. Micro is -6, nano is -9. Does anyone know what 1 over 10 times 10 to the -9 is? What frequency that is? Okay. Say it in megahertz. How many megahertz is this? Close. Further away. Wrong direction. He said 10, he said 1. He's going the wrong direction. Yeah, it's 100. There we go. Yeah. Plug it in a calculator, you'll see it's 100 megahertz. And the reason why we use this 10 nanosecond period, 100 megahertz frequency for the simulation is because that's what the Basis 3 board runs at. Okay, it runs at 100 megahertz. Okay, so when we separate the test cases by 10 nanoseconds, we're essentially doing a test case for every clock pulse. Right, because you get a clock pulse every 10 nanoseconds, or it's running at 100 megahertz rate on the Basis board. Okay, so that's the reason for those numbers, in case you were wondering. Alrighty, so the next thing is I would go ahead and copy and paste the Verilog code of Mealy's for the time multiplexer out of the text file. And again, remember to put it into a Verilog file, not a system Verilog. If you put it into system Verilog, you're going to get all sorts of red lines, right? Because again, things like wire and reg are not part of system Verilog. So Vivado will not like it if you do that. Another common error that's made, and I'm not exactly sure how this happens, but what will happen sometimes when people paste into the Verilog file is they get wraparound. And what I mean by that is in Mealy's code, there's lots of comments, right? Because he's a really good coder, right? He comments everything. And sometimes what happens is like a comment will get split up. And recall that in System Verilog and also Verilog, if you have double backslashes, what follows is a comment. So what can happen is like the comment gets split up, like half of it gets put on the line underneath it, and it doesn't have the double slash. So then it's being interpreted as a code, which doesn't make any sense because it's a comment. And that causes all kinds of errors. So just be careful about that. I mean, I can't tell you how many times I have someone, they go, oh, Mealy's code is not right. I put it into the file and all these errors. We have used Mealy's module for like 10 years. We know it's good. So if you're getting all kinds of errors, it's not the module, it's something in the translation. Okay. All right, so once you have all this done, then you go ahead and you make your structural model, right? Your top module that's going to tie this all together. Like I said, I would start with the lab 4 structural model and just edit from there. Now, the overall test cases, they're on Canvas. And the test cases for lab 5 are the same test cases as lab 4, but you have to additionally show that memory works and that reset works. Right? So you're going to have a main reset button or clear button, whatever you want to call it. You also got to show that the enter works. Okay. You'll know if your memory is working when the switches change, like say you have it loaded onto your board, on the basis board. Well, if your memory is working, as you're changing the switches to a new test case, the display should show the old result. The display should show the old result until you hit the enter button, right? Until you hit the enter button with a different couple of numbers that you're either adding or subtracting. You know, if you're moving the switches and as you're moving the switches, your numbers are changing on the display, that means your memory is not working. Okay. And then of course, to check your reset, right? You just hit the reset button, display should go to 0. Check your enter button. When you hit the enter button, that's when the display should update. Does that make sense? Okay, and when you simulate it in the simulator, it should also show the same as what you would expect on the board, like you've seen in other labs. All right, this is also very important. All right, so make sure you make a note or highlight, or I would definitely, if I was a student in this class for today's lecture, I would take a picture of everything that's up on the board here before you go, just to make sure you don't forget it or you forget to write it down. Okay, remember Dr. Benson's troubleshooting video. Okay, what was the big technique? Like, what was the big thing out of that video that you learned and that you demoed to me?
Drag and drop.
Right, that you can take any intermediate signal, drag it onto the timing diagram. And, the reason why Dr. Benson titled that video troubleshooting video, because that's a very useful technique to troubleshoot, right? Because you can trace the signal through your circuit and see where it first goes awry and, zero in on where the problem is. Well, in addition to troubleshooting, that technique is necessary in this lab in order to see if your overall design is going to work. Because the output of Mealy's module, his time multiplexer, the SEG and AN, when you look at it on the timing diagram, it's not going to make any sense. It's just going to likely be the same value for all of time. And that's because the simulation has a limitation where it can't show time multiplexing. It just doesn't have that ability. So what you have to do to verify that your overall design works is you have to look at what's going into Mealy's module, right? See, there's input CNT1, and look where that input connects. It connects to the Q output of that 4-bit register. So what is that 4-bit register storing? Where does its D input go? Like if you follow where the D input of the 4-bit register connects, where does it connect? Okay, so T5, the output of this MUX, and what data is at the output of that MUX that used to be going to this decoder that you deleted? Yeah, that's the binary number. That's the result, right? The 4-bit result. So that top register is storing the result of either your addition or subtraction. How about the middle register, which is really just a flip-flop because it's only storing a single bit? What's it storing? Because look at where the Q output of that goes.
The sign bit.
Yeah, it goes to the sign input of Mealy's module. So it's storing the sign bit, right? Whether you have a positive or negative. Look where the D input goes, T6, which is the output of that AND gate, right? And remember, the output of the AND gate, That's why it identifies whether your result is positive or negative. And then look at the bottom register. Again, it's really just a flip-flop because it's storing 1 bit. What's it storing? Where does its output go to? Yeah, see, that's the validity bit. It's going to the valid input of Mealy's time multiplexer. And look, T7 goes to the output of the validity checker.
If we have an input into what is this called?
Time multiplexer.
Time multiplexer.
Well, it's labeled universal SEG, but it's doing time multiplexer.
That,
Okay.
if we have a validity, like the output of a validity checker going in and a sign bit, do we need the AND gate in the old puzzle?
Yeah, you still need this AND gate because it's going to generate that output only when it's valid and negative. You know, that's when it will generate a 1 that tells.
Right, for the,
Yeah.
okay,
Yeah, because the way Mealy's module works is that if the sign bit is a 1, it's gonna light up a dash on the furthest to the left 7-segment display. So instead of an LED lighting to show it's negative, you're actually gonna see a dash on the furthest to the left 7-segment display. And then your result will be on the furthest to the right display. Okay. If it's invalid, okay, let's say, well, first of all, if it's valid, it will show whatever the result is. But if it's invalid, say, 0, that will cause dashes on all 4 7-segment displays. Okay, so instead of like blanking like it did in lab 4, it will show dashes. Okay, now look at the CNT1 of Dr. Mealy's module. It's 14 bits. And it's connected to a Q output of this top memory register that's 4 bits. So what did we call that? In fact, it's written right on the sheet. When bits don't match. Yeah, see, we have a bit mismatch or bus mismatch. And several weeks ago, you did an activity that dealt with, this mismatching of bits. And do you remember how you could solve it? That you could essentially make the bits equal? Right, and you would add it to what side of the binary? Left side. You don't change the value. Say that again?
On the other side of the.
Yeah, exactly, because you don't want to change the value, right? But what in Verilog allows you to do that? Like what in Verilog allows you to add bits to the left? You can even do it to the right, but in this case, we want to do it to the left. You remember the term concatenation, right? Yeah, remember concatenation is the same as joining bits. So that's what you should do in your code. And, you may have to look back at that activity that we did several weeks ago where, it had examples of concatenation. And that's when you're using the braces, and inside the braces, that's where you put what you want to join. You got to separate it with a comma. Okay, so, that's something from a previous lecture that you might have to go back and review if you need to. All right, so let's see, where are we at here? We've done all this. Okay, we're going to come back to this. Yeah, I told you about that. Talked about what the register, that's the 4-bit register, storing the number. This is storing the sign bit. This is storing the validity bit. We just talked about the mismatch. These key inputs. Check that out. Okay, so there's just 2 more things we need to talk about, unless you have questions. Okay, let's talk about this next. Okay, looking at this diagram here, notice that the main clear input goes to the clear of the 4-bit register. It goes to the clear of the flip-flop that's storing the sign bit. But then look at this bottom register that's storing the validity bit. The main clear is connected to set. It's not connected to clears of that flip-flop. And I can't tell you how many times, and I can understand this mistake because it's an understandable mistake, but it's still a mistake. I can't tell you how many times that somebody will look at this and they'll go, oh, Perks is always screwing up. That can't be to the set. I'll just connect it to the clear like the other ones are, because that's clearly a typo. But it's not a typo. When we're clearing the 4-bit register and this flip-flop that stores the sign bit, at the same time, we want to set this flip-flop that's storing the validity bit. Can you guess why
You want to have a set or, yeah.
Right, because what should display when we hit reset? What should the 7-segment display? Because when you reset, what happens to the output of the flip-flops? Go to 0. So when we reset the entire circuit, we want the 7-segment display to show all zeros. Well, it's only going to do that if your validity is 1 while your reset is active, right? If your validity wasn't 1, if it was 0, the display would just show all dashes. Okay, so that's why you see set connected to the main clear. Okay, because we want the output of that validity check flip-flop to go to 1 when we reset, so the zeros will be shown. And again, I can't tell you how many times I'll get emails and they'll be like, Gary, everything works, but when I hit the reset button, I get dashes instead of zeros. And it's because they connected to the clear instead of the set. Okay. Now also notice that there's these ground symbols, right? Those of you that had circuits know what the ground symbols or ground symbol looks like, right? And what's the voltage at ground? 0. So you just set those inputs to 0 wherever you see ground. Okay. All right, the last thing, unless you have questions, is when you do the constraints file for lab 5, and remember lab 4 was the first lab that you were dealing with the 7-segment display, and I gave you a handout, hopefully you still have it or you have a picture of it, that shows you how to number the segs and the AN. Okay, everybody know what I'm talking about? Okay, well, because of how Dr. Mealy designed this time multiplexer, when you do the constraints file for lab 5, number the seg and the AN reverse of what you did in lab 4. Now I can't remember, in lab 4, does it go 0 to 7 and 0 to 3, I think? Does it go in like from top to bottom? I think it goes 0 to 6 because you had 7 segments in lab 4, and then 0 to 3 because you got 4 AN. Okay, so if it's like that, you just go the opposite direction in lab 5. Okay, and also remember, seg is now 8 bits, so you would include the decimal point. You know, that would be your 0, I think. I think the decimal point is 0, then it goes 1, 2, 3, 4, 5, 6, 7. The opposite direction of what you did in lab 4. If you go the same direction as you did in lab 4 and lab 5, you're going to get all gibberish. Okay, and that's just because when Mealy declared his inputs and outputs for the time multiplexer, he did it against convention. He called his most significant 0 and his least significant 7, just the opposite of what 99% of humanity does. Okay, for whatever reason, he did it that way. I don't know why, but he did. Okay. All right, so I think we've talked about everything up here that I wanted to talk about. Do you have any questions? Because at this point, and even before today's class, you had enough information to do lab 4. So again, that's the priority. If you're not done with lab 4, work on that. Let's do this Friday. But you now have enough information to do lab 5. Okay, and again, lab 5 is not due till end of next week. So, you have like a week and a half. Okay. Next class, this Thursday, I'm going to talk about FSM, okay, finite state machine, just an introduction to that. You won't have enough from that one lecture to do lab 6, but next week I'll give you enough information where you can even do lab 6, okay, which is the last lab before, the final projects, which actually it works out kind of nice this quarter because lab 6 will be due the Friday right before the Thanksgiving break. So you'll have Thanksgiving break, and then the 2 final projects are due the 2 weeks after. So if you're really on the ball, you finish all the labs, you finish lab 6 on time the Friday before Thanksgiving, you could actually do your final project over Thanksgiving if you're not much of a turkey eater. And, you could be finished early. I'm not saying you have to do that. I'm just saying that's a possibility if, because, turkey makes you tired. That's, that, right? It's got what does it have? Turkey has that chemical that like puts you to sleep, right? What is it called? You know what I'm talking about? Or yes, it does. It has like some chemical that makes you sleep. No one's heard of that? It's kind of like the natural, well, melatonin is the natural, right? That brains generate. Is it turkey? Yes, it is. It's got something in it that puts people to sleep. It puts me to sleep. All right, so that is all we have today. So, I understand if you just had, I was like that when I had a midterm, the last thing I wanted to do was work. I used to go home and sleep. So if you want to do that, that's fine. But I'll be here till 6, and also Ratchet is here. If I have questions on lab 4 or any other questions.